Hello guys, so today we'll take a look at the maximum power transfer theorem. This theorem states that a load will receive maximum power from a network or circuit or whatever when the load resistance is exactly equal to the Thevenins resistance of that network. Thevenins resistance of that network. Now we know that Thevenins resistance is equal to Norton's resistance, so you can replace this with Norton's resistance and it will be the same. And so in an equation format, max power when RL is equal to RTH. Okay, so this is the main theme, that when Thevenin's resistance is equal to when the load is equal to the Thevenin or Norton's resistance, we will get the maximum power from that network for the load. And the application of this theorem is if we want to determine or if we want to estimate the maximum power that a network will provide to the load, then we can use this theorem. So to estimate uses to estimate max power possible for the load, or to determine how much power from the circuit a load is consuming. So if we are given RL, then we can determine what power RL is consuming from the circuit. So these are the uses of the max power transfer theorem. Another use is to estimate what load conditions will provide or will draw the max power. Now let's practice a couple of questions using the maximum power transfer theorem. So at first we have determine the load condition needed for maximum power transfer in this theorem. So remember, for max power, RL must equal RTH or R Norton. Okay, so first thing we'll do is apply the Thevenin's theorem or Norton's theorem and find RTH or RN. It's all the same thing. I just mentioned RTH from now. So we remove the sources, short circuit for voltage, voltage source, and then the resistors, and this is the open load terminal. We have R1 3 ohms and R2 6 ohms. Okay, RTH this way. So what do we have for RTH? RTH is equal to these are parallel, so R1 parallel to R2, 3 parallel to 6, that's 2 ohms, I presume. Yeah, that's 2 ohms. So we can write that for maximum power, max power RL is equal to RTH, so 2 ohms. Okay, so when we have 2 ohms here, if we have 2 ohms here, then we will get the maximum power, the maximum load condition for then we'll get the load condition for max power. Okay, now let's see the next question. If RL is equal to 10 ohm, what is the power draw? Okay, 1, 2, let's just go to the next page. So to RL is equal to 10 ohms. So what is the power draw? Now we know that power draw is P is equal to I square R, right? Now for this theorem, we will put L's here. PL, IL, RL. L indicates the load, okay? So PL means the power draw at the load, and RL means the load resistor, and I square L, IL means the current that is flowing through the load. Now to find IL, we have another equation. IL is equal to ETH over RTH plus RL, okay? So this is basically the total internal resistance of the circuit, because RTH is all the resistance except the load, and you add the load. Now we have RTH from the previous question. We had RTH is equal to 2 ohms, okay? And we have RL given, that's 10 ohms. Now we need to find ETH. Where's our circuit? Our circuit is here. We have to find, and this, the voltage given here, this is not ETH. This is just the normal voltage source. We have to find the Thevenin's voltage for this circuit. Now how do we find that? The same steps. First we find RTH, which you already did. Then we take the circuit as it is with the sources. Okay, and then the resistors, the open load terminals. So here we have R1, that's 4 ohm, that's 3 ohms. 3 ohms, R2 is 6 ohms. And here we have 7 volts, okay. So ETH is the voltage across the 6 ohm resistor. It's actually the voltage across these terminals, but that's in parallel with 6 ohm, so it's the same. Now, how do we find that? We use the voltage divider rule. So V1 over R1 equals V2 over R2. Here V2 is the total resistance, so V2 is equal to E is equal to 7 volts. And R1, V1 is what we'll find, so we can write Vx over Rx equal to V2 over R2. So Vx is equals, we will find this, so Vx is the voltage across R2. You can write VR2 is equal to 1. And Rx is R2, so that's 6 ohms. And R2 indicates total resistance, so RT. And total resistance is, of course, in series here. So that's R1 plus R2. That's 3 plus 6, so 9 ohms. Okay. So rearrange Vx, just write V2 instead of Vx, because that's VR2, equal V2 over R2 multiplied by Rx, which is R2. Okay. So that's 7 over R2 is 9 multiplied by, sorry, yeah, R2 is R total. Yeah, this 9 over, I should just write R total here. Okay. Multiplied by R2, which is this one. So 6 ohms. 7 over 9 multiplied by 6, that's 4.67 volts. And this is ETH, because it's the voltage across this place. So we have ETH equal to 4.67 volts, and we have RTH, we have RL, so we'll find IL now. IL equal to, let's write it down again, ETH over RTH plus RL. ETH is 4.67 volts over RTH is, where's RTH? Here, 2 ohms. RTH is 2 ohms, plus load resistance is given at 10 ohms. So calculating that, we have 2 plus 10 is 0.39 amperes. Okay, so what's PL? PL is the maximum power flowing drawn by the load resistance, which is 10 ohms. We have IL squared multiplied by what? RL multiplied by RL. IL squared multiplied by RL is equal to, so IL squared is 0.39 squared multiplied by RL, whereas our RL is 10 ohm as given, equals 0.39 squared multiplied by 10, that's 1.521 watts. Okay, now this is the PL, so you can write PL 10 because that's for 10 ohms. When RL is 10 ohms, you have power at 1.521 watts. Okay, now let's have another question. Let's just make up another question, 3. Compare max power. Let's write compare PL, or just write compare power at max power load conditions. So max power load condition, which is what we found in question number 1, and at 10 ohm load. Okay, so at 10 ohm load, we just found PL 10 ohm is equal to 1.521 watt, right? And in question number 1, we found that for max power, we'll have RL as 2 ohms, right? RL equals RTH, which is 2 ohms. So at max, we had RTH is equal to 2 ohms, RL is equal to 2 ohms, okay? And ETH is the same, since we are doing it on the same circuit, which was here, 4.67 volts. 4.67 volts, right? So what will be IL here? IL equal to ETH over RTH plus RL. That's 4.67 volts over 2 plus 2. So 4.67, 2 plus 2. 1.17 ampere, okay? And so PL at max, PL max equals IL squared multiplied by RL again. IL squared is 1.17 squared multiplied by RL, which is 2 ohms here. So 1.17 squared multiplied by 2, that's 2.74 watts. Okay, now look, PL max is 2.74 watt and PL 10 ohm is 1.521 watt. So of course PL max is greater than PL 10 ohms. Why? Because this PL max is the maximum power that this network can produce. And to get that maximum power, max power possible in this network. And what's the condition to get this network? RTH equals RL. Actually, it's supposed to be RL equal RTH, but you get it's the same thing. Because RL is our effect and RTH is the cause. Okay. R is equal to RTH. So that's the condition for maximum power transfer, and this is the maximum power transfer theorem. And remember, RTH is equal to Rn, so it's interchangeable.